This is
This is Colorado. This is PyCharm.
I'm not gonna get you think I'm joking.
So what I'm doing is I'm trying to force like
Okay. So we're running out of seats as we gain more and more people for these. This is great to see. But so last time we didn't quite get through all the demos for parallel computing, and I know, and I still owe you because I'm definitely far too late on this, but I have to fix the kernel situation for the code spaces. How many of you are trying to run on code spaces for this semester versus locally?
Code space.
Most people are going code spaces. Okay, great. Then I'll make sure that we have that up and working, and I'll record a little video. It'll probably take me like 3 or 4 times to figure out the exact steps that you need to take for when it does get wonky. I think about 1/3 of you had like success, and 2/3 of you had it just didn't work that time, and that happens. It's for what it's worth. GitHub provides you free resources, but they also give you a headache. What was the other thing I was going to say? Last time we talked about parallel computing a little bit, and sort of how and why we wanted to talk about why we wanted to at least have an understanding at the high level of like the memory hierarchy of computer architecture and why that affects us. Again, most of what you need to do for research for this class, for whatever you do in the future, does not need you to understand low level computer architecture, but just having this idea about the memory hierarchy of speed can help you design better algorithms and to understand when algorithms do break down. So we really looked at this for about 10 minutes or so, was using Dask for parallel computing with Python, and I probably just confused all of you by saying the word like futures a bunch and being like, this is what it does. So I'd like to revisit some of that code stuff today, even if you're not necessarily able to run it right away. So I'd like to do that. I would like to talk about Xarray and its data representation. So this is Xarray is a Python library that is used for geospatial data, and we'll use it a lot for this class. But beyond that, it sort of encodes this idea of dimensions, coordinates, attributes that I think is really important for thinking about data more broadly. So who here, is anyone not familiar with Dask? 1, 2, 3, or sorry, Xarray. No, changed my mind. Okay. Is anyone not familiar with Xarray, at least as a first idea? Okay, everyone's got Xarray down. Excellent. That makes my life easier, and hopefully yours. Okay, so we're going to go through this parallel computing with Dask again really quickly, and then I'll talk about Xarray a little bit. But since you're mostly familiar with it, I'll glide through it, but I think it's worth talking about some things, and we'll do a little board exercise. And then last, I wanted to show you the Dask dashboard. Given, I think half of you said about no Dask, I think it's worth showing the dashboard just for you to wrap your head around being able to understand if your algorithms are set up correctly or not, and that will relate to the board exercise. So again, parallel computing, most of the time, we can compute stuff faster than we can feed data into it. So we try to run things simultaneously. And Dask is about the, oh, right, I still didn't fix this slide yet. So Dask is about sort of the standard way to do parallel computing. There are other libraries, again, for parallel computing with Python, but Dask is just easier than all of them and more flexible and works sort of transparently with Xarray. So that's the reason we're going to use it. So what we did last time was we talked about you can get your client, which just is like the thing that manages all of the computation. This is sort of when I had in the slides that like complicated graph of like dependent computation. Dask is what figures that out for you, and we'll actually be able to see that in a moment, how it does it. So we talked about the low-level futures API. Can anyone remember why it's called a future?
It's a lazy operation that we will execute in the future.
The lazy operation that will be executed in the future. So when you submit something to the client, it doesn't do anything. All it does is put it in a queue or some graph structure to say like, we'll do this later. And only when you hit the like compute function does it actually do anything. So we saw that here. So the first time, again, it runs 2.5 seconds. This time it runs 1 second or so. And I'll run it real quick. But again, it's something that's worth, taking time to wrap your head around. So when you submit it, nothing happens. All that gets done is you say, I want to run this at some point. With Dask, you get out this future thing. So this future is what you want to run, and then when you actually run it, you ask for its result. There are different languages around this. There's result, compute, persist. So there are a bunch of words around this that you'll kind of just get used to. And that's when you actually get the result out, when you call .result on it. So you can also run, we talked about the idea of putting together the task graph, which is if you have multiple operations that you want to do. But then really the last thing where I kind of feel like I didn't quite get through was this chunking idea, right? So can anyone explain the idea of chunks? I mean, I know the answer's on the screen, but you can just shout, yeah.
So rather than having data as one full unit of measurement, it's compiled into smaller chunks that are stationed elsewhere. It's a more decentralized.
Decentralized, I like that word, yeah. And again, tying this back to all of the junk that we talked about with computer architecture, like why do we want chunking?
You don't want to just like pull in a huge data set every time you want to do that for computation or something.
Yeah, so this is why you can run things in parallel. It also means that if you aren't running things in parallel, you don't have to load the entire data set to look at one thing at a time. And so we'll talk about that in a second. So Dask arrays are very similar to NumPy arrays, but they have this chunking operation, which we saw sort of at the very end of the last class. So if you had something that's like a global 1 degree data set with a year of daily data, it would have this shape, right? Time, lat, long are your dimensions. And then you might chunk it up like monthly and into, I don't know, like roughly, 8 sort of quadrants is what this sort of does. And I just instantiate some random data in there. But again, talking about this in memory, like when you load this into your system RAM, it's all there, right? Like when I create this is technically all in memory already. So we're already like pretty fast, right? Remember, again, you kind of lose an order of magnitude of access speed at each level, but RAM is fast. So it's all in there. But the thing that's nice about having chunked arrays, even in memory, is you can still do things in parallel. So that's where we're talking about this embarrassingly parallel, where nothing depends on anything else. you can just run the computations, and I actually don't think I ran this, so. So you can just run everything sort of on its own. So if you look at this, what we're going to do is we're going to convert it from Celsius to Fahrenheit and then calculate an anomaly. And what you can always look at is the Dask graph, and I'll show this in the dashboard in a second, where you can visualize it sort of more intuitively, but you can always access it with this function. And here you can see we have 704 tasks. So tasks are sort of like, it's not exactly independent computation, but it's for all intents and purposes that. So if you had, 704 cores on your computer, you could run them all independently. Of course, we only have 4 on, well, I guess I don't really know what my laptop has, like 12 or something, but on the code spaces by default, you'll have 4. Okay, so we can compute that. Again, compute is, where'd it go? Compute is sort of like asking for a result. It's the same idea. So we calculate that anomaly, and you can see it does exactly what you'd expect it to do. And it ran that all in parallel. So, okay. Right, I kind of lost the plot here. So there's 2 other things that are sort of more nuts and bolts, I guess, not super theoretical or anything like that. But again, we talked about sort of the idea of a map operation, right? Does anyone remember what the map operation sort of does?
We have an array kind of does an operation on each element of the array.
Yeah, yep. So a map operation is taking a sequence or some iterable, something that has a bunch of elements and applying the same operation to all of those elements. The sort of other counterpart that is often used as a reduction or a reduce operation can, I mean, it's kind of said there, but can anyone explain that like idea intuitively, or give an example of one that's not shown on the screen currently?
Like a sum of an array.
Yeah, sum is a reduction. So what does a reduction fundamentally change about the data?
The size.
Dimension, size, yep, exactly. So you're taking some data set and reducing its dimension or its shape by at least 1 or more. So a total sum would be like going from n dimensions down to a scalar value, right? That's a reduction. And so that's what we show here. It's fairly boring, so I'm not going to talk about it. And then the last thing that I wanted to talk about, that's again more nuts and bolts, is this idea of map blocks. So X-ray and Dask come with a lot of built-in operations, but often, if you have some complex algorithm, some radiative transfer, some advection dispersion or something that you want to run over a big data set, you're going to have to write it yourself, right? And to run it in parallel might not work out of the box. So this is the last thing that I don't think we're going to ask you to do very much with this, but it's worth knowing. So this idea of map blocks are the chunks. I don't know why they couldn't keep a consistent terminology, but here we are. So here I'm just doing some very dumb calculations, but basically, well, just replacing outliers with names. So all it does is check for a reasonable temperature range and then map anything that's outside of it to nans. And again, we have some function we call map blocks on it. So this is a custom function. We give it to map blocks, and then we tell it what we need out. So temperature here is the array, right? Map blocks is something that you can call on an array. And that's how you schedule it to run in parallel. So again, you'll see 416 tasks and nothing has been run, right? Took 0 seconds to run that. Okay. We can run it, it does its thing. No problem. Okay, so the last thing that I wanted to sort of, and I'm not even going to, I don't think I'm gonna run any of this code. Yeah, maybe we'll talk later about best practices. Okay. So what this, all of this code will eventually walk through. Maybe I should figure out a way to screen recording here. Okay, so if you think about all this chunking, all this parallel computing stuff, why does it matter besides running your code faster? Like, can anyone think about how you should lay out your data for some sort of analysis? Like, what's the ideal chunk size?
Depend on what you're trying to do.
Yeah.
Let's say you want to calculate. Let's say you have some dimensions by time and you want to calculate the average over time, then it'll like collapse the time dimension. It'd be better to chunk it in such a way that each chunk has the full time dimension preserved. I don't know if I'm making sense.
So this would be like an annual mean or something.
Yeah.
Okay, so what are your input dimensions?
So
Maybe?
you have long time.
And what are the output dimensions going to be?
For now, let's just assume that we only have 1 year of data.
Sure, yeah. That's
Then you'll go down to lat long.
okay. What other sort of operations could you do with this sort of data? Oh, you're not gonna be able to see any of this on the video. Sorry. It's like garbage. So going like taking an average over time is one thing where you reduce out the time dimension,
Maybe regrading the data
regrade to a different.
resolution.
Okay, yeah.
It can be spatial or temporal.
So I'm going to make the distinction when you say regridding, it means space. Aggregation or disaggregation would maybe be usually the time word, but you're not wrong. It could technically the operation is the same, just the word we use is different.
Yeah.
Okay, so what does regrid look like?
Yeah, new that and long, but the time will be same.
Put a hat on them.
Probably something similar for average also. Put a hat over time.
Now,
You have a good point. Yeah, average over time could be a total reduction, or it could be a what other type of operation could you do for that? Like a rolling mean or something that would give you the same time, or if you did from daily to monthly, would give you a different time coordinate. Okay, we'll leave that one. That's not bad. I'll just say like zonal statistics might get you from So I know this is getting boring. You got the idea. So you might reduce out or change the shape of just the latitude or whatever. What the question that I really want to talk about is what is the most efficient chunking scheme for each of these? So let's start with average over time. And I think maybe you already kind of said it, so don't say it again. What would make your computation most efficient if you wanted to go from lat long time just to lat long?
Over time,
Chunking in time.
chunking over time.
Chunking over that time. You should have the full time and chunk it over the.
Yes, exactly. So yeah, if you're going to sort of reduce out one of your dimensions, you want to be able to chunk over the other ones rather than the one you want to reduce out. Because then you can run each of these separate, you can run your zones in parallel. Does that kind of make sense?
Go chunking in lat and long, and then we're just leaving time.
So it's better if you're operating over all of your time to have time as one chunk because it's going to go into the same process no matter what, right? And by process, I don't necessarily mean, specifically a CPU or anything, but like just thinking about from a generic compute perspective, like if you want to average over all times, you need to look at all times first, right? And you don't need to look at every latitude and longitude. So these are the ones that you can sort of say are independent. So it's thinking about for your algorithm, which dimensions are independent, right?
But then the time is so big also, and the goal is averaging, so it doesn't matter. Can we, for example, do the chunk over all 3 dimensions? Because at the end, we should do the average over all the chunks. At that time, we should consider chunking the time too also. When, for example, the time is 40 years hourly data. Is it wrong if we do that? If we chunk over time at that time?
But then you need to compute independent chunk and then yeah. So you will
One time averaging, you're doing 3 times, so you know.
Also depend on functionality.
the final operation will depend on the chunk. So the final time average will depend on the individual time.
Okay, I like this question. So just saying we have like 1 degree gridded data for 40 years of data. Well, let's go with the hourly. Can someone tell me roughly how big this is? Like, or
There are 300.
okay. And yeah, let's also run a quick. How big would that be? We can screen back on since this recording is garbage anyway.
I think we need to remove the background smooth to show the board.
I did. Okay, if we're talking about double precision 64-bit floating point number, that would be this many bits times 64. And make this only 8. So this array would be approximately, I hope that I did that right on the fly, 180 gigabytes. So Hussein's question is a very good one. Like, if it's bigger than memory, like, what do you do, right? But again, if you have it chunked up in both space and time, you can reduce the chunk size, right? Like, these are, I'm sorry, this linker is as good as I thought it was. So these are our DIMMs of lat long time. On average, your computer has 8 to 32 gigabytes of memory, probably. If you work on a big server, it might be in the hundreds, but typically not more than a terabyte of memory. This is 180 gigabytes, so if you're on a big server, you could load the whole thing into memory. And the question is, then what's the best way to chunk this up so that you can actually run computations on it? Does anyone have any suggestions? If we wanted to do this operation again.
I'm not sure, but I normally do over 3 dimensions.
Mhm.
Because if you just do it over the left alone, and again, if you face the memory crash, you have to decrease the chunk for left alone. And after time, doesn't make sense, you know. You should make a lot of chunk if you just make the left alone smaller and smaller. So maybe it's better to chunk the time and
So, let me,
In that case, if you do it in that way, you will have a series operation at the end. But if you do it only that one, you will have only parallel operation.
so imagine if you do the left alone, so it will crash, and then you should change the chunk for the left alone again. And at one point, you see, okay, you are chunking 10 by 10, and it doesn't make sense. Maybe it takes more
But
than
it could
time.
be one by one and do everything in parallel and avoid any
But-
series operation.
Okay, one by one, but that means more time. But maybe if you do it over the time, and at the end, at that, maybe time you can save more time.
I would take one time, because if you do one, all of it are parallel, but it takes one time. to-
Exactly. And the other one should be independent, parallel, and a final series to compute the final average.
If you chunk over time, the first of the process is not sequence. So it's work at the bottom, but if you do it over the left line, even one by one, it's a little bit more parallel. It will be more faster.
okay, I really like this discussion. So someone who's not saying Aldo, which one's better? Can anyone say for sure?
That's all.
What is an array of 350,000 on its own in terms of memory usage?
One take forever. Okay, so. Does it close chunk? If you were to do that one by one, because you doesn't remove. One K. Yeah, or is this one more?
Never really calculating averages. Just a big chunk.
Okay, I'm hearing some good discussion here. The answer is we don't know. Because of many things. Again, the memory hierarchy of your computer is going to matter a lot in doing this. First of all, second of all, there's a trade-off between coordination, even in when everything is embarrassingly parallel, when you're using scheduler type parallelism, there is a cost to every individual task. So this will incur many, many more tasks than this, even though theoretically, technically correct, these can all run in parallel, should be faster. Because if you have infinite parallelism, you can do everything at once. Technically, that's not true. We have memory, not just at the system level, but at the CPU cache, those L1, L2, L3 that we talked about. So if you just look at the time series, it's was it 2.8 megabytes per time series. Typically what you want your chunk size to be is somewhere between 50 and 200 roughly megabytes. So that's just a rough guideline, and that's just because it's easier for the CPU to actually do stuff with it. When you have very, very small chunks, what you end up doing is a lot of transfer between your CPU and your main memory in a way that's not super efficient, especially with these schedulers like Dask, which are not. And it's like, I really want to emphasize this. Dask is not the most efficient way to do parallel computing by any means, but it saves you a lot of headache. And so that's what I wanted to sort of emphasize here is the chunk size is not necessarily dependent on only the parallelism. It is a function of both the scheduling software you use and the hardware that you're on. And it's, again, usually more of a function of system memory and CPU cache than it is the actual algorithm, unless your algorithm is very compute intensive. But if it's something simple like an average, it's probably more storage than it is compute.
So, I mean, this is like so out of my realm, so this might be a super stupid question, but so we have like a 180 and a 360 right there, and we're breaking them both into tens.
Mhm.
Won't we be like recomputing the 180 several times if we do that? Or should we be
Let me say,
I don't know if that makes sense, but
that's supposed to be a number sign. Okay, good question. So if I have 10 by 10 chunking, then the number of chunks, and that's what we were looking at. I'll scroll up to find it again. So there would be 18 of these, 36 of these, and 1. Right? Does that say what you're trying to explain?
so would we, because we run the, I don't think I'm fully understanding. Okay, so we're gonna run
Then, yeah.
so in one, let's just say like in one single computation, you make a 10, 10, and a 1.
Yeah, let's call this the task dimension or the task dim. And I think this is what you're asking. Okay. So for every task, it would be 10 by 10 by 350,000, right?
Mm-hmm.
And so the total number of tasks is just the product of all of the chunk pieces, I guess. So it would be number of tasks would be 18 times 36 times 1. Does that answer
Yes.
or explain?
Yeah, so you're just computing all that. So you have 18 times 36 times 1, that's the amount of tasks that you have.
Yeah.
And each one of those, you're computing one of those task dimensions.
Yep, exactly.
So that doesn't actually matter, like the total size of like the 180 and the 360, because you're just computing them all in each task dimension.
It does in terms of like, if you doubled your grid resolution in one way, it would double the amount of computation, but.
Mm-hmm. But like in each individual computations.
Yeah, exactly. Every task would be the same size.
Yeah, I think I was thinking of it wrong. I think I was thinking like if we break them up into like 10 and 10, I thought we were going to compute like the 180 faster than the 360, but then we're not collapsing those.
Right.
Okay.
Yep,
So it's
yep.
making more sense.
Okay, cool. And this will become more intuitive, probably in the last half of class rather than the first half. Okay, so let's talk about X-ray for a second. And then I'll show you the Dask task scheduler as quickly as I can, just because I think it's worth knowing how to open. Okay. X-ray is a library that uses Dask and NumPy and all of that stuff under the hood. It's a great representation of multi-dimensional arrays. And what I mean by multi-dimensional is you can have lat long time, you can have variables, elevation, anything you can think of as a dimension of data, you can include in your data structure. Oh no, I don't have Pooch in this yet. I'm thinking. Okay, I know that was entirely illegible to all of you, but there we go. Okay, so it seems like most of you were at least somewhat familiar with X-ray. And so the main ideas of X-ray, just to formalize this, are that data sets have 4 things in them, more or less. They have dimensions, which are the labels for each of the array axes. So, and this is sort of our time lat long that we talked about. It could be things like ensemble members. If you're doing stochastic runs, it could be things like different physics parameterizations. If you're using a multi-physics thing, it could be depth. It could just be, you know, like sites. So if you don't have lat long, it could be different like point locations or things like that. Dimensions are how you attach labels and meaning to the actual dimensions of your arrays. Coordinates tell you specifically sort of where, when, how of something. They're considered sort of more like metadata. They're still data, I guess, but your actual data variables, the things that you are either measuring, modeling, or you know, whatever, are in your data variables. And then the last piece of that, and those data variables are functions of either your dimensions or your coordinates, probably both. And then lastly, you have attributes which describe the data. So in this case, what we did was opened up a tutorial data set, which is a reanalysis of essentially air temperature. So it has air temperature every 6 hours, I believe. We can look at that. So you can open any of this up, you can click and yeah, so it's every 6 hours. So, you know, it's January 1st at 6 a.m. rather than midnight. Okay, so that's the super high level overview. Again, when you're looking at this, you can look at the DIMs, you can look at the individual aspects of each dimension. You can pull out anything that you want. It's much like a Python dictionary. Same with the coordinates. So again, coordinates and dimensions. Dimensions are just the labels and the sizes. The coordinates are the actual like timestamp or the latitude that's given to you. Computing functions over X-ray data sets is very transparent. You can just run operations. So here it's air pressure at a certain height and temperature, just using the standard equation. And you can just spit that out. So this is all very transparent. I encourage you to run this on your own and go through it. For the sake of time, and mostly because you all were fairly familiar, the last thing I wanted to talk about was this Dask dashboard. Can anyone see why it works in one notebook but not the next? All right, we can use it here. I think I just broke my whole environment. Hold on a second. Okay. And, there we go. Okay, so the last thing I wanted to show you, and again, this is just more of a like, you should see it, to see it more than like, I'm gonna quiz you on in the future. When you create a client with some compute resources, it will, by default, sort of create a thing that does the management in the background, and there's a user interface to this that you can see in the dashboard. So if you're running this on like your laptop or something, like I am here, you can just click this. If you're running it on like a remote server, you may have to open a port to actually like pass back the computation or the I guess the network. So in this case, what I can do is I can open this up, and this is a very handy little guy that what we're looking at here is we have the total memory that's stored. You have the workers. Each of these little blue bars is a worker. Nothing's happening right now, so it's totally blank, right? And it has task processing, a general progress meter, and then the task stream, which is the biggest part. So you should know that it's the most important. And we will be looking at this more in depth as we do data loading for machine learning stuff. So let me get this out of here. Okay, so if I open up a data set, okay, maybe I will just do it on this part. Okay, so again, 4 workers, and we're just running some simple computation. So that first time, nothing happened. Again, that was me running in serial with no Dask stuff. So the second time I will do it. And what you see here is this is a very simple task stream where you can see all four pieces sort of ran on their own. One of them took twice as long as the others, probably just for synchronization. And you can see it took some amount of memory. This isn't as fun as the example I wanted to show you, but again, I broke my environment by adding something on the fly. The other thing that you can look at, oh, here we go, is the graph. Again, the graph here is not going to be very interesting, right? All of the tasks ran independently, so they're just a little dot. So we can do something that requires more processing. So this, these are the old ones, so you can ignore them. But you can see the task graph gets made dynamically by Dask, where it has to do essentially 3 total parallel operations and then 1 reduction operation. So the reduction is because you have multiple nodes coming into one, right? Does that make sense? Okay. I'll show you a better demo of this on Wednesday in the first couple minutes, but then we'll move on to linear algebra finally and talk about now computers. Cool. All right. Thank you.
Did you record the lecture on Friday?
I did. I just haven't posted it yet. Yeah, it, I uploaded it, or I haven't uploaded it yet. I always forget.